All right. Solenoid valves. Solenoid valves seem fairly simple. They are pretty simple. Got a coil sitting on top of an enclosing tube. You've got this plunger with a pin that pokes into this hole. And in its simplest form, liquid's coming in here, and it's going up and it's resting and waiting for the energizer. The energizer of this pulls the plunger up and opens a hole, lets refrigerant through. Now, there's a problem with this design. You can't make them very big. The reason you can't make them very big is because the greater the pressure is on this side, you got to figure there's a certain amount of area. Let's call it 1/10 of a square inch. Okay, that 1/10 of a square inch is the pressure from one side to the other side. How much would be exerted on there? So let's say it's 250 over 50. That's 200 pounds across that hole, right? So that 200 pounds across that hole is being exerted on 1/10 of a square inch. So how much is that? It's 20 pounds per square inch being exerted on that pin, trying to shove it through the hole, okay, from one side to the other. The magnet that's inside this, that pulls up on this pin, has to exert enough pressure or enough pull to pull out that 20 pounds per square inch. Okay? If we increase that to 2/10 of an inch, or 3/10 of an inch, or 3/8 of an inch, okay, we're talking about a hole that's so large with the amount of pressure that can exert, it can't pull the pin out of the hole. So it's called maximum operating pressure differential. Now you get to a point where you have maximum operating pressure differential issues. I think you have other issues besides that. Okay, but that's about it. But that's why there's direct acting solenoid valves like this and pilot operated valves like this. A pilot operated valve has the same plunger and pin assembly on the top, but you've got this disc in here that rides up and down inside this journal. Okay, the pin holds it down in a hole, holds that hole closed. Liquid can come up and go around that whole pin, or that whole plunger, and go up to this hole and fill this whole area up in here with liquid refrigerant. So all the red area is liquid refrigerant waiting for that pin to be pulled out of the hole and go downstream. So when it's energized, it pulls the pin up, the liquid refrigerant goes downstream, expands, the pressure difference between one side and the other is decreased to 0, and the liquid coming up here and pushing against that disc lifts it off the seat and it floats. It floats on what? It floats on the flow of the refrigerant going through there. So it needs to have 1.5 to 2 pounds of pressure drop across it to have the velocity as it makes that turn to float that disc. Okay? So that's why it's important that they be sized correctly. If you get too large of one, the hole's too big, there's not, and this disc is so large that the lack of flow, the decrease in pressure drop means that you don't have enough velocity to hold that pin, that thing up floating. So these are subject to the other side of the coin, not maximum operating pressure differential, but minimum operating differential. Minimum being about 1.5 pounds. You can go 2, you can go 3, but that's the difference between one and the other. So it really does make a difference when you go into a wholesale house and you ask for a 3/8 solenoid valve. I hope you're not the guy that says, "Oh, I don't care. I need a 3/8 solenoid valve." Well, the counterman should be saying to you, what's your refrigerant? What's your tonnage? Do you want a manual stem? What's your voltage? Because it's all sized by those things. What refrigerant, what tonnage. We make 7 different sizes of 3/8 solenoid valve, and 6 of them are wrong for your application. Okay? So that's the difference. You got to have that information on you. So, what's next? Sight glass. Exciting, right? I'm going to spend the next 20 minutes talking about the sight glass because it's so important in your system. What does a sight glass do?
Window into the system.
It's a window into the system, a window into tomorrow. Yeah, all that stuff. Okay, yes, it's a visual indication of the quality of the refrigerant that's behind it. You can look at it through a window. It has a little bullseye in there. If the bullseye is evident, that means you got all vapor. If the bullseye is not evident, that means you got all liquid. Okay, kind of cool, huh? So, yeah, it gives you that, but what else does it do?
Tells you whether there's liquid there. Tells you whether there's liquid there.
Well, it does tell you whether it's
dry,
the quality of the refrigerant, whether it's liquid or vapor. Yeah, it's going to tell you that, but there's another thing that tells you.
Stacking up refrigerant?
When to stop adding refrigerant?
It tells you whether it's dry or wet.
You say it has a little wet, dry.
Side glass. Okay, side glass with a moisture liquid indicator inside, right? That's what it is. Okay, well, let's talk about POE. POE is, basically used for all HFCs. It's used in almost everything now. The POE is not as scary as it used to be, but it still needs to be taken care of because it's very hygroscopic. Hygroscopic meaning it picks up moisture, a lot of moisture, really quickly. If you look at just POE sitting in a bucket, mineral oil and alkyl benzene, you get up to about 1,200 parts per million just sitting there. Now I have heard people say that, oh yeah, I filled that cup full of POE oil right to the top, and by the next morning it was flowing over because it picked up so much moisture. I'm like, yeah. Right? It's like 100 parts per million of mineral oil and alpha benzene. Basically, they sit there inert. They don't really pick up a lot of moisture. It has to be just entrained in it. Where POE actually picks it up and does something with it, and that's why it picks up all that moisture. Because making POE is a hydrolysis of esters. In essence, it's taking alcohol and acid. Sounds like a party from the 70s, doesn't it? Takes alcohol and acid, puts them together, combines them together, and the byproduct is ester acid or ester oil and water. Now, you can reverse that by putting the water back in the ester oil, and it will turn into alcohol and acids again. It turns into its component parts. That happens at 75 parts per million. That's a key number right there, 75 parts per million. Okay, so the reaction is reversible. It can actually occur. But what does that really mean? When you go down through all these calculations, 75 pounds of water to 1 million pounds of POE down to 75 parts per million is really 0.7 drops per pound. 0.7 drops per pound is the level that stuff starts to break your oil down. So you put it in a perspective, a half-force condensing unit has about 1.5 pounds of oil in it. You're only talking about a little less than 1.5 drops of moisture in that oil to make it turn into ester acid and alcohol. Now, when you talk about those two things, ester acids and alcohol is not a big deal. Alcohol can be picked up by the dryer in the desiccant. Alcohol has been added to refrigeration systems over the years called thaw zone, I believe. And it basically keeps ice from forming at the expansion valve outlet. But the ester acid is another thing. You guys work on 134A systems with POE and cap tubes? Any experience with that? Okay, what you're going to find out with 134A with POE and cap tubes, especially if you have high discharge temperatures, maybe the possibility of a clogged condenser, that kind of thing, you're going to end up with cap tubes that are plugged with gray matter, gray stuff, okay? The breakdown of the oil into an acid, the acid attacks metal surfaces inside the system. When it attacks those metal surfaces inside the system, it turns them, it gets this salt. Okay, it's a eutectic salt or something like that that resides on the metal, and then POE is very polar. In other words, it works very well as a good solvent. It cleans that stuff right off and carries it downstream with itself, carries those salts downstream until it finds a place where you have a phase change. Where does the phase change occur? Cap tube, expansion valve, all those things. when we first started going from 12 and 22 and 502 over to these other refrigerants, and they were asking about, oh gosh, what's this stuff on this expansion valve metering pin? What's that stuff? Like, don't know. Sent it back, still didn't know. Chemical engineer gets a hold of it and says, well, it's this salt stuff. So that's what's happening. So with the cap tube systems, the 134A and cap tube systems, there's guys that just absolutely will refuse to use those darn things because they gunk up with this stuff. It's like a heart attack. It's just happening, you know. So anyway, that's why it's important. That's why I spent the last 10 minutes talking about a sight glass, because it's important. The thing that you're looking at is a color change. Sporlan changes from yellow to green, right? You've seen those. Yellow if it's caution, and green if it's good to go. Well, when it changes green, it's 120 parts per million per their literature. 120 parts per million is 45 parts per million over the threshold that the oil can break down. It doesn't get any greener. All it does is say green, you're under 120 parts per million. Our last color change on an Emerson sight glass, and it's the only thing I'm going to try and sell you today, that last color change is at 25 parts per million. 3 times drier than the level that you'll break down the oil. So it's important that you do use a quality sight glass when you're dealing with POE oils, and you're always dealing with them, so there's no reason not to use them.
I have a question. You mentioned earlier a bullseye, so you can tell the difference between a dry sight glass and a wet, not liquid, not moisture, but vapor versus liquid, a
Right.
solid column. I've never heard the bullseye.
It's the same in sight glasses in compressor. When you look at the sight glass and compressor, if you can
In
see
the glass?
in the
In the
glass,
glass, okay.
yeah. If you can see that bullseye, then the oil level's below the eye. And if you can't, then it's above it.
Seen those on other sight glasses?
Yeah, I've never seen one on a sight
One
glass.
time I used it.
Yeah,
Yeah.
I haven't seen one on a sight glass.
Really?
Besides
Because of that, but maybe not now.
yeah.
level.
The HMI does it, yeah. So this is just a graphic you know, of what's going on with the yellow changes. So I think this one is a Defrost, that one's a Sporlan, and there's ours, an Emerson one. So, all right, one of my favorite topics: expansion valve. I can talk for an hour, no, 2 hours. On expansion valves. How'd you like that? No, let's not do that.
I've been there. I've been to that one.
Okay, so seeing as how I do know what an expansion valve is, I'm going to point out the major things that are going on. Basically, you've got 4 pressures that's being exerted in your expansion valve that drives that expansion valve to control your superheat. It does the same thing that you do when you test for superheat. It takes the pressure of the line, and it takes the temperature of the line. The part that takes the temperature is P1. That's the bulb that's on the outlet of the evaporator. It's got liquid refrigerant in it. It's got a ballast in there as well that's made out of different things like marinite crystals, molecular sieve, paper, cigarette butts, stuff like that. We put in there to soak up the refrigerant at different rates. It makes it release that refrigerant at a different rate. So, you know, a lot of the difference between the charges that we have on these expansion valves is just how fast they respond. Okay, like a C charge, commercial range charge, has a range of refrigerants that, can I draw on this?
Yep.
Okay, because that one says do not draw on. Okay, so if you're trying to hold superheat right here, okay, you're trying to hold that, say, at 10 degrees, and you got 1 refrigerant in your bulb, it's going to go like this. And you're only going to be at 10 degrees at a particular, like 25-degree evap. If you're below or above that, you're not going to be able to hit it. You're going to be lower. So what you've got is you've got several, just like the glide of a refrigerant, you've got 3 different refrigerants, maybe even 4, that come in like this. And it gives you a linear line of capacity control, or of superheat control that's much wider. maybe from -10 to +50. Make sense? So that's what the bulbs do. Okay. What that means, but I don't know. But anyway, so we're taking the temperature and we're bringing that down to this diaphragm right here. That diaphragm separates between the temperature and the pressure side of this valve. The pressure comes back on the equalizer, the external equalizer, and that's the pressure of your line. So let's say, for instance, your line is 50 degrees downstream. That bulb is now 75 pounds. This equalizer line is 50 pounds coming back from 50 degrees. Fake refrigerant, right? And then you've got to have an additional closing force, because this is an opening force, the only one at 75 pounds. The equalizer is coming back at 50 as a closing force. You got to have how much pressure on this guy? 25 pounds of pressure on the superheat adjusting stem. So as things change, temperature goes up, pressure goes up in the bulb, drives the valve open, feeds more refrigerant. When it feeds more refrigerant, refrigerant boils off, pushes back on the equalizer line, and closes the valve. Tries to close it. So it achieves equilibrium and balance between the temperature and the pressure at what your superheat adjustment is. That's the part that you can mess with right there. Then P4, pressure, that fourth force is the liquid pressure coming through here, trying to get from the high side to the low side. It's trying to drive that valve open, and we'll talk about that in just a second. As a matter of fact, right now. So if you have a fan cycling system, fan cycling for head pressure control, what you're doing is you're shutting the fan off, and the fan shuts off, and your head pressure goes up. And then you turn the fans on, and head pressure goes down. It goes back and forth like that. When we're at the low event of 150 pounds, we look at this valve sitting here at 150 over 50, we have 100 pounds of pressure drop across that port, trying to get from the high side to the low side. So if that port is 1/10 of a square inch, how many pounds of pressure is being exerted against that? 10. 100 pound delta P is 1/10 of a square inch, is 10 pounds per square inch being exerted on that. So, in order to compensate for that, you're not doing it because, oh, I need 10 pounds, pressure. You're just adjusting your superheat, but you're going to tighten that and adjust it and load it for the 10 pounds of pressure that's against it, right? So, unknowingly. So the next thing happens is you're at the high event. 200 over 50. Now you're 150 pounds of pressure drop across that port. You've preloaded for 10. The pressure is now what? 15, right? So it's got 5 pounds of additional pressure being exerted against it, where you've loaded for 10. It's going to drive that valve open. And when it does drive the valve open, it's going to overfeed. And when it overfeeds, what's going to happen? It's going to try and close. Equalizer line is going to come back and say, oh, we've got too much refrigerant. So it starts this hunting cycle. You guys seen that, I'm sure. So when it's hunting 6 degrees to 14 degrees, 6 to 14, 6 to 14, you just average that out and go 10? Right? Yeah, that's about right. Because I think that's what a lot of people do. They're satisfied as, well, it's supposed to be 10, so, and it's really right close, so I'm just going to leave it alone. But what's happening in a lot of cases, most of this is because of oversized expansion valves, because the expansion valve doesn't know what's downstream of it. If I take, I'm just going to do a little bit of something different here. I don't know if you can even see this because I write so darn small. Okay, so we'll just do something different. I've got a evaporator that's 9,000 BTUs per hour. Okay, that's a cooler. 9,000 BTUs per hour. How many tons is that?
3/4.
3/4 of a ton, right? Because that's 3/4 ton. Okay, now I've got an expansion valve box. It says that I've got a range of 3/4 to 1.5. Is that right? Should I use that valve because it says 3/4 on that 9,000 BTU evaporator?
It's oversized.
Absolutely, it's oversized. In its own little world, that valve it's like a 50-ton valve on a 25-ton evaporator. You guys understand that? That's not gonna work right. You got dead compressor coming. So what I'm pointing out here is a serious inequity in what's going on with some expansion valve manufacturers. Okay, so this guy says, extended in balance port F valve R22 externally equalized A range. Okay, that's the A range that it runs at, 3/4 to 1.5. The double A range is from 1/3 to 1/2. Neat thing about that is, no, it's from 1/4 to 2/3. That's what it is. 1/4 to 2/3. Actually, that 2/3 valve is the proper selection for 9,000 BTUs. But this happens a lot because guys just look at the box and they believe. Man, it says 3/4 to 1.5 tons. There's no such thing as a wide range valve. What it means is that if you've got an 18,000 BTU evaporator and all of your load falls off where you only have 9,000 BTUs left being exerted on that coil, it's going to the coil, then that valve will not hunt. That's what it's saying. It's saying it'll hold it, it'll maintain it. So that's where I'm going. Don't judge the whole book by its cover. All right. So balance port valves, no magic, just a better way of making a valve. That liquid pressure that I was talking about was trying to get through to the downstream side, actually can hydraulically push against the bottom of this shoulder right here and down on the pin, and it balances out the effect of head pressure difference. So as your head pressure changes from high to low, your superheat stays stable. All right, cap tube. I don't think we need to talk about cap tube. The longer it is, the less you get out of it. The smaller it is, the less you get out of it. You got a large one, short, you get a lot out of it. It's like a 3/4 inch hose against a 1/2 inch hose. Okay, hot gas pressure regulators. Hot gas bypass. What's a hot gas bypass really do? Well, do I need to explain this to you? Hot gas bypass?
For defrost?
Anybody? No, it's not for defrost, it's for capacity control. If I've got, I'll just take it quick here. If I've got a 20-ton evaporator here, and I've got a minimum load, that 20-ton evaporator or unit system is doing this room when there's 200 people in here. And then, now there's nobody in here, but I still need to do some air conditioning. All the loads cut out, what happens to your suction pressure? It drops like a rock. Then you ice up an evaporator, and you end up having to go out and de-ice the evaporator to get these guys cooling in their room when they got the 200 people that walk back in. Okay, so what this does is, for the minimum load of the room, you bypass however much you need to. If it's a 20-ton evaporator, 20-ton system, let's say you got a 4D compressor running on it, okay, and you got one bank of unloading, okay, that 4D compressor with the one bank of unloading means that you cut down from 20 tons to 10 tons, right, when you unload that one bank. So you go down to 10 tons, your minimum load is 5, you bypass 5 into the inlet of the evaporator, you're at 10 tons. You're at that minimum amount. So that's how it works. It keeps the evaporator, it keeps the suction pressure up to keep it from getting into that freezing range.
So back to the TXVs. So what's all the information you guys need from us if we were to call and say we need a TXV but we can't get one from the factory for some reason, for you guys to build us one, or for us to build one if we had the TXV kit?
Any wholesaler, thermal supply can do that for you.
Okay. Do you know what information they require? Just basic nameplate
Need
stuff?
to know the
or-
refrigerant?
We tried building one last summer in emergency buying, and they're asking a bunch of different stuff, and I'm wondering what's actually relevant to building one.
Okay, what's relevant to building one is, of course, the refrigerant,
Yeah.
the evaporator temperature range,
Okay.
the tonnage that you need, that you require, how much subcooling you have, and subcooling is only if it's mechanical subcooling. If it's natural subcooling, in other words, a cool day, you don't calculate that. You let the valve make up the difference. So that's really it. You only need refrigerant, tonnage, let's see, what did I just say?
Saturation temp.
Yeah, subcooling if necessary. And, that's pretty much it. Refrigerant tonnage, subcooling if necessary, and connection sizing.
And then they can just build any TXV you want, right?
Yeah. I mean, they probably have it in stock. I mean, don't you guys stock like up to like 20-ton valves?
Us?
No,
Oh,
Yeah, he's like, where do I get that? It's on your truck.
Don't carry one of
Well,
them.
the Reaper guys in the class have the kit, so if they're on service call, they build wherever they need. Done.
Well,
Buy the kit.
Thermal has kits, we have kits. I mean, ours are a little better mousetrap, but I'm not here to sell you anything, okay? I'm here to talk about refrigeration. They can definitely hook you up with a kit for every one of your trucks.
Seth?
Yeah, it's cool. We need a TX.
All right, so-
Class. Parts order in there.
So here we are, we're getting close to the end, guys, hold it together. EPRs, evaporative pressure regulator. What it does is it holds back the pressure of the evaporator so it doesn't get out of whack. Usually it's used with applications where you've got, let me get back over. The heck? Am I missing a slide here? Okay, all right. Here's a good one. Okay, this is good. An EPR, your flow's going this way. Basically, this is coming out of the evaporator. There's a tap here, so you can tell what the pressure is in your evaporator. But all it's really doing is there's a spring up here you can adjust. You take the cap off, you reach in with an Allen wrench, you tighten the spring until it's the right pressure upstream. And the pressure as it rises in the evaporator is going to push on this poppet and come on through. That's all it does. It's simple stuff.
That's a lot larger, like.
No, really.
With the multiple evap's on one compressor system.
Oh, yeah, but not really. I mean, you might be talking 5 horsepower. If you got one walk-in that's sitting there with 2 horsepower running it, and then you've got a bunch of reach-ins and stuff like this running out the same thing, that's gonna actually give you different range temperatures going out to all these different ones. And that's another beauty of digital scroll or digital application, is that we can match the capacity even if you cut out all those reach-ins as they satisfy on their box stats. You can decrease the capacity of the compressor to match it, so you never have to worry about that minimum. So, but really here we're talking about having an EPR in this minus 35 ice cream evaporator, and then one that's set for the poundage of minus 30, and one that's set for the poundage of minus 20. And then this common section would be, what would be the common suction pressure going down through here?
Right before the compressor?
Yeah, from here.
Minus 30-ish.
Well, it's definitely going to be minus 35, less another couple pounds, because it takes a couple pounds just to operate these things. So minus 35 would be, because if you're around minus 30, minus 35 wouldn't flow into it. It has to be the lowest pressure,
Below the,
lowest pressure that it serves.
plus the minus 35. Above the minus 35.
Jake, you're confusing me.
Never mind, below the minus 35.
I know, it's a lot. Okay, so here's another application though. Take a look at this. Feature a convenience store that has an L-shaped walk-in box, not walk-ins, but glass door cases. Okay, you got 10 glass door cases going down this way, you got 4 going down this way in this convenience store. You got two different sizes of evaporator. You got one for the long leg, and you got one for the short leg, with one condensing unit. In that application, you could use an EPR on both of those, so one does not run away with the other. Okay, and that's all it really is talking about here is making sure that you stay at plus 25. You set your EPR here for plus 25, that one for plus 25. When that one's continuing to refrigerate and this one's icing up, this will stop. Okay. Defrost. You guys deal with defrost clocks like this much? Oh boy. Got any questions about them? This is really messed up. So.
Oh, boy.
Oh, man.
So these guys here, you use the grasses or you use those, you use the electronic ones? Both? Yeah. Which do you like best?
Top one.
The top Paragon?
I'm old school.
I know, they've been around forever, right? Okay, well, you know, when you're talking about defrost adjustments, you know, it's one of these things. It's basically, you're gonna go 2 to 4 defrosts a day. You don't wanna do it during a time of day when people are working in there, you know, that kind of thing. You wanna make sure that your fail-safe setting is not too long. That's this dial on the inside. If you set that in the wrong spot with too long a defrost, what happens?
Gets hot.
Get a lot of steam.
Oh.
Steam comes out in the freezer, that steam comes out and it freezes to the roof. When it freezes to the roof, when you do have warm air coming out again on the next defrost, it starts dripping on the floor. When it drips on the floor, what do you got? A lawsuit. Okay? They call them lawyer puns. Because you walk in there and you're laying down all of a sudden. So, you know, that's also true of the termination temperature. You want to make sure your termination temperature is adequate to defrost the coil, but also to be able to not have too much steam occur. So, you know, when you're talking about using a defrost termination thermostat, it's nice to have one of the adjustable ones, like an F25107 Renko. Those things work pretty good. Because you can adjust your termination temperature and also have a differential that's going to get you down to the two things that the defrost terminator does is one, terminate the defrost on which terminal of the thermostat of the X, because that comes back to the X. Okay, and that terminates your defrost. But the other thing that it does, what does it do?
Turns off the fans.
The fans were turned off when you started the defrost through the terminal 3.
Liquid line solenoid valve?
Well, no, liquid line solenoid valve's on 4. You de-energize that whole circuit down through there. What it does is when it gets to the bottom, it's differential. It's a 55 with a 20 degree or 30 degree differential. Okay, 55 is a termination. 25 degrees is where the fans come back on. Fans come back on at 25 for what reason?
So you don't blow water.
So you don't blow water, exactly right. That's the rest of the lawyer pond story. Because, you know, if you've got a bunch of water sitting on there and the fans are off, you've got to re-refrigerate that back down to 25 degrees to make sure it's frozen back onto the coil before you start the fans up. Because when the fans start up, it's going to blow squirt stuff all over the room. So that's what it's all about. I'm not going to spend any time talking about these guys. Although there's a whole big old presentation on it, I just am not going to. Yeah, this guy right here, these are great. You know, you can put them in there instead of this 3-wire job. You can pull that out and run the 3 wires to this. You know, when one goes to X, one's common and one's terminator, or the fans. So, next thing, CPR, crankcase pressure regulator. Anybody know what that's for?
That one's for defrost, so you don't have too much like slugging or something. It has something to do with defrost instead of bringing it back to the compressor.
That's partially it.
That's why I'm here.
Yeah.
I knew it like this.
No, it's because of overloading the compressor. When you come out of a defrost, the expansion valve is gonna be what? It's gonna be wide open. You know, it's gonna try to be wide open unless you've got some other means of doing it. But it's gonna be wide open, so you got a bunch of liquid refrigerant that's gonna blow by there. If it's correct, and it's still got superheat, your pressure's gonna still come up pretty high in the compressor and overload the compressor. That would be evidenced by tripping on the overload, things like this, watching your amp draw. When you set a CPR, you usually do it by amp draw. Whatever your compressor is supposed to be running at, whether it's minus 20 or plus 25 or whatever it is, you calculate what the amp draw is supposed to be there and set the CPR for just a couple amps above that. So the back pressure coming back is adequate for the compressor to work. And then as the back pressure, as it catches up, then it allows more refrigerant to come through again. Make sense? Okay. Ball valves. I don't think this crowd needs to hear about ball valves. Why is that one there?
Servicing the accumulator and the suction
No,
direction?
because we sell them. No, that's true. That's what it's there for. When you shut off the service valve on a compressor, you shut that ball valve. You can draw the moisture, or actually shut that, pump it out, and you can bring it down to vacuum or atmosphere and change your cores. That's pretty much it. EPRs, ball valves, dirt. Okay. Accumulators. Why do you have an accumulator?
To make sure you don't slug that compressor.
Darn straight. And for what reason? I mean,
Does it blow it up?
heat pumps, yeah, it will. Heat pumps especially have the same problem. When they do reverse cycle defrost, the hot gas goes to the evaporator bulb first, so it's hot. It's like 240 degrees, and so the expansion valve is wide open. When it comes out of defrost and it goes directly into air conditioning or heating again, it comes ripping down through here, through the outdoor coil. That's not very far to the compressor. So you need to have something to stop that liquid refrigerant before it gets to the compressor. And the way it does it, simply put, A is the inlet port. It misses, it doesn't go right into it like this. It misses it, actually has a deflector in there that deflects it away as well. But it swirls down through here, comes back up, goes in that, and then goes by this pitot hole and out to the compressor. That hole's there to get oil back off the bottom of the accumulator, because if you didn't, or if it's dirty, it's going to accumulate all the oil that's in that compressor, and you're going to be putting another compressor in, then another compressor in. So, you know, if you have problems with the repeat failure, and it appears to be locking up, you might consider changing your accumulator as well on an air conditioning application. The refrigeration application, you know, not so much problem with that.
How come?
How come?
Yeah.
Because-
How come refrigeration doesn't have as much of a problem?
Cleanliness. I'm just saying. HVAC guys, I'm sorry. When you talk about 5 tons and less, I had a guy talking to me today, he says, do I really have to change the dryer? I've spent 24 years talking to people about this stuff, and to have somebody ask me that question, I said, I don't care, just do what you want.
More job, just so.
Sell more compressors.
You're gonna do what you wanna do anyway, you know, so just don't tell me about it. I did say the compressor's out of warranty, isn't it? He goes, yes it is. I said, great, thanks. Okay, replaceable core filter dryers. There's a lot of different kinds of cores that are for different things. I think what this kind of keys to me, you've got brass ones for suction service, you've got steel ones for liquid line service, and they come up to 400 cubic inch with 4 100 cubic inch cores. while I'm talking about cores and what they're made of, that kind of thing, well, I'm about to. What do you think about charcoal? What's your thoughts on charcoal and filter dryers? HH cores. Let's bring that.
We had a problem with the compressor at some point.
Well, just wondered about, how you felt about HH cores. Charcoal, does it do something for you? If you go into a wholesaler and say, I need an HH one.
Yeah, when they ask the right questions, I give them the right answers. And
Okay, well, so why do you want an
some
HH?
questions.
Why do you want an HH?
For severe burn.
Moisture.
Most of the time, that's exactly what it is. Most guys are worried about severe burn. The thing about HH cores is that they, of course, have charcoal. Charcoal has an affinity for one thing, and that's wax. Okay, wax is a byproduct of low temperature R502 refrigeration from the 60s. That they originally incorporated charcoal into the filter dryers to pick up the wax, so that, because at minus 20, 502 in mineral oil, there's a flock point of the oil. The paraffin would fall out of it and go downstream and then get stuck in things like expansion valves, solenoid valves, and what have you. So the charcoal took care of it. When that whole problem was over and the manufacturers were making mineral oils with flock points around minus 50, they didn't need it anymore. But they left it in there. Why did they leave it in there? Because when you put burnt wood in the place of something that actually does work, like moisture removal and acid removal, you put 20% charcoal in there, what are you going to take away? What's working for you or what's working for you? That's the whole story right there. We make an HH as well because people just are stuck in that stigma.
Well, what about like wax coming off of windings when you're running high low tension stuff? Is
long-
it gonna pick that up?
Coming off windings is long chain polymers that are picked up by effective filtration. It's not
So
something.
charcoal won't help that.
No, if you consider what desiccants are, okay, desiccant is a sodium cation with a 3 angstrom hole, okay, and 3 angstroms is very small. It's like 3/100ths of a micron or something like that. It's about the size, well, it's the exact size of an H2O molecule, okay? H2O molecule fits in that. Acid has the same thing. Acidic compounds get trapped in macro and micropores in other types of desiccants. We use those as activated alumina. Charcoal is the same thing. It's like this. It's like if you got a screen door that has holes in it that are the same size as the flies you're trying to catch, they stick. But bumblebees don't. Okay? So that next level up is something that is active filtration. And that is 20 micron, well, 3 to 20 micron filtration. Picks up those things, the burnt windings and that smoke kind of stuff. So, make sense?
Yeah.
Okay. With that, that's what I got for you guys.
So
Any
what's a recommended?
Yeah, are we going with a filter?
It's not HH.
Yeah, actually, a UK, something that's blended properly for POE applications. Copeland's recommendation is 75% molecular sieve that picks up moisture and 25% activated alumina that picks up acid. Okay, Emerson's blended that way as a 20 micron filter and the proper blend of desiccants to make the proper blends. And the reason for that is that you know that there's one kind of oil that we approve for use in our Copeland compressors, MA32, RL32MAF is what it is. And it has a package of additives that make it more miscible and make it more lubricious. In other words, it'll travel better with the refrigerant and it stays on bearings better. Those additives are acidic in themselves, just like the POE oil is. So if you use too much activated alumina, it strips those additives out of the oil and changes its makeup. Okay, does that make sense? So what I'm saying is, blended correctly, per Copeland specification, you don't strip as many of those additives out, and it still is able to do its job. Now, Our enviable competitor lives there 60/40. So that's outside the specification. So you make your own determination.
So that's just a catch-all filter. You know, there's no high moisture, high acid.
Catch-all
that's
filter.
it.
Catch-all filter has a high acid capacity.
So it's all high acid, high moisture. It's all that's what you
High
got-
acid, low
what
moisture.
you got going on.
If you're trying to get moisture out, you're using the wrong thing.
Okay.
And they don't filter very well.
Sure.
40 micron instead of 20. So I said I wasn't going to do that. Stop me before I kill again. Okay. Thanks, guys. Appreciate you coming. Putting up with me for the past couple hours.
Yeah. Any questions? Jimmy?
I appreciate your.
Suction limiter.
Yes, what?
So my valve is a suction limiter. By design, are we talking about that is, are we an EPR or?
Suction limiter. Are you talking about those valves we're looking at?
Yeah.
Those are EPRs.
Okay,
It depends on, it really depends on where you're, because those valves were very universal. They have a pilot tube that comes off on one side or the other. If the pilot tube is downstream, then that's what it's sensing and reacting to. If it's upstream, it's reacting to that. So,
yeah, now I gotta look at that.
most of the time they're upstream pressure.
Covered number to.
Well, this is a
And
weird
you're just
system,
thinking,
so it's like-
send me a number.
I gotta look at it, but I guess essentially, so, well, setting that thing, I mean, somebody before me has made an adjustment, I'm just trying to
But
understand.
you know where the adjustment is, that G865 pilot, little cone thing looks like,
Yeah,
you know, on that is a screw. The tighter you tighten it, the more it pushes down, the higher the pressure goes upstream.
okay.
So,
Perfect.
yes.
Well, I'm gonna try something when I go back there.
So Friday we'll be talking about.
Friday, I may be doing some troubleshooting.
The fun with the chambers you're doing?
All right, thanks, guys.
Thanks, guys.
So with the headmaster, is subcooling even relevant at that point, or are you just looking at your sight glass?
You're just looking at the cycle. Yeah,
Because you're not gonna get like a real reading.
you're gonna have a ton of
You're
subcooling.
just stacking the liquid, right?
Yeah, it's gonna be,
You're just stacking the liquid up and then cooling it, so your subcooling is
Right, so your numbers are gonna be like.
yeah,
You're like, oh.
you got minus 20 air blowing
Yeah,
out.
I got 60 degrees of subcooling on my overcharge, but I'm bubbling in my sight glass.
Make sure you document that. I don't know, I'm pull mine out.
And then those EPR valves, are you just looking at what you want your evaporator temp to be? No, like a cooler, you're looking at 25 degrees, and then you're gonna convert that to a pressure, and then that's what you're gonna set it for?
This can be read.
We'll get into it.
That's what I-
So my impression was that I was working on this PG, and the next pressure goes to and somebody told me that they pumped.
That next?
So there's a high limit.
Somebody left some batteries over here.
Batteries charged already?
No, but
I didn't think.
Peel or mineral plate.
Okay.
It's
in mine.
Tear down the crack box compressors is gonna be awesome.
Company up north,
Oh, you can do it now?
Lodestar, that does a lot of.
a certain percentage.
It's gonna work.
Which operator and what is what?
So they were just
If
purchased
you're
by
going to
one
a
of my
POED
HVAC
oil, you
companies.
have to
They
have
can have
95%.
That would be a plus option as well. Maybe I'll hit.
That's what I said, I didn't train says up to 95%
set up to 95?
has to be changed out, so.
Yeah, we'd have to.
So we'd have-
So yeah, on that Scott T compressor, so basically, I went to a job and, it was all medium temp, walk in, and it kept, tripping the overload. And it was running fine, a few weeks before, did a maintenance on it, everything seemed fine.
95.5.
So I opened it out.
One is one of that
And
compressor. If,
We're just
so
doing
that could also.
I can't remember what happened. So it seemed like, so it looked like it was stuck.
Yeah.
It wasn't tripping the breaker, but it seemed like it was physically just seized.